The first starship to Proxima Centauri may leave Earth carrying 100 pioneers, but after decades trapped in deep space, it could arrive with empty seats. The first death may strike years before the destination is even visible, exposing a hidden weakness capable of turning one tragedy into the loss of the entire crew. Today, we will uncover the most likely breaking point of humanity's first interstellar journey and whether the survivors could stop the mission from collapsing completely. Let's begin. Proxima Centauri is the nearest star beyond our sun. That sounds almost comforting. It is only 4.25 light-years away, close enough to appear on the same neighborhood map, close enough that a signal traveling at the speed of light can reach it in a little more than 4 years. But humans cannot travel as signals. If a crewed spacecraft moved at 10% of the speed of light, the simplest calculation would suggest a journey of roughly 42.5 years. That number is accurate. The ship must accelerate. It must eventually slow down. Its engines cannot operate outside the limits of fuel, heat, structure, and human endurance. The most credible mission would therefore last closer to 50 years, perhaps longer, depending on how those two demanding phases are designed. And during all that time, nothing can be delivered from Earth. No replacement pump, no emergency medicine, no rescue vehicle. Imagine crossing an ocean in a vessel that can never enter another port. The distance matters. But so do the engines, the drinking water, the spare parts, the health of the crew, and the ability to stop when land finally appears. Proxima is the same problem expanded beyond every voyage humans have ever survived. To investigate what might kill the first person aboard, we need a specific mission. Otherwise, every answer can escape behind a different assumption. So, this journey carries about 100 people. The ship cruises near 10% of light speed. The mission lasts approximately 5 decades after acceleration and deceleration are included. The crew lives and works in rotating habitats that attempt to provide artificial gravity. There is no suspended animation, because reliable human hibernation does not exist. There is no faster-than-light communication, and there is no hidden supply station waiting between the stars. This is not a prediction of the ship humanity will build. It is a reference case, a common measuring stick. It also establishes an important rule. The first death during the voyage is not the same as the first failure of the project. A propulsion design may prove impossible before construction begins. Funding may end. A launch accident may destroy the vehicle near Earth. Those outcomes would end the mission, but they would not answer the question being investigated here. Our question begins after departure. The ship is committed. The crew is alive. Earth is receding. Which part of the journey is most likely to turn a functioning spacecraft into the environment that causes its first human death? The obvious suspect seems to be distance. Yet, distance never touches the hull. It does something more subtle. It removes help. When the ship is halfway to Proxima, a distress message takes more than 2 years to reach Earth. A reply takes more than 2 years to return. A broken valve cannot wait that long. Neither can internal bleeding, smoke in a cable bay, contaminated water, or rising carbon dioxide. The crew must diagnose every urgent problem locally. They must possess the tools, knowledge, materials, and authority to act without permission. A spacecraft near Earth can be supported by thousands of specialists on the ground. This vessel must carry the practical equivalent of that expertise inside a population smaller than many apartment buildings. Then there is the destination. Proxima Centauri b is real, but much of the world people imagine around that name remains unknown. The planet completes an orbit in about 11.2 days. Its minimum mass is close to 1.05 times the mass of Earth. Those facts do not tell us whether a crew can breathe there, walk there, grow food there, or even descend safely through an atmosphere. We do not yet know whether it has a durable atmosphere at all. We do not know whether liquid water waits on its surface. Its star is active, and the planet circles close to it. Calling it Earth-sized is not the same as calling it a second Earth. That distinction changes the mission. The ship cannot merely survive until someone sees a planet through a window. It must arrive with enough functioning machinery, healthy people, stored knowledge, and remaining energy to study the system, choose a safe location, and respond if the expected refuge does not exist. So, the investigation begins with 8 suspects. Propulsion could fail while building the enormous speed required for the crossing. Waste heat could overwhelm equipment that has no surrounding air to cool it. Interstellar gas and dust could strike the forward shield at extreme velocity. Radiation could damage cells and electronics year after year. Low or imperfect gravity could weaken bodies. Life support systems could lose control of oxygen, carbon dioxide, water, or temperature. Disease or injury could exceed the limits of the onboard clinic. And several small failures could connect, producing a crisis that no single backup was designed to stop. Each suspect will be judged by 4 questions. How early can it appear? How quickly can it become fatal? Can the crew detect it before people are harmed? And after it begins, can the ship recover? Those questions matter because dramatic hazards are not always the most dangerous ones. An impact is terrifying, but it may be rare and obvious. A sensor drifting slightly out of calibration may look harmless, yet it can quietly guide an entire system in the wrong direction for months. The first ranking is therefore provisional. Propulsion and heat stand at the entrance to the mission. Dust and radiation wait along the route. Gravity, medicine, and human biology apply pressure slowly. Life support operates every second. Cascading failure connects them all. Nothing has killed anyone yet, but the ship has already lost the protection that made every earlier human expedition possible, a nearby civilization able to intervene. Before it meets the first grain of dust, before radiation accumulates, and before a recycling system begins to age, the vessel must accomplish the act that creates almost every danger that follows. It must reach its chosen speed. At 10% of the speed of light, 1 kilogram of moving spacecraft carries roughly the kinetic energy of 108 kilotons of TNT. That is several times the explosive yield of the bomb dropped on Hiroshima. Now, imagine a ship with a mass of 100,000 metric tons. Its motion alone contains about 4.5 times 10 to the 22nd joules of energy. They must remove almost all that speed. Speed appears to be the solution because it shortens exposure to radiation, equipment aging, and decades of human isolation. But speed is not free time. It is stored energy, and every additional kilogram makes the bill larger. The crew feels none of this while cruising steadily. A cup rests on a table. A person walks normally inside the rotating habitat. Constant velocity does not press anyone backward. Acceleration does. If the ship could maintain acceleration near 1 Earth gravity, the human body might tolerate the force well. There is nothing automatically lethal about that level. People already live under 1 Earth gravity every day. Its engines must push an immense structure without twisting it. Their thrust must pass through frames, joints, tanks, bearings, and habitat connections. If the force is even slightly misaligned, the ship may bend like a long truck whose rear wheels suddenly shove sideways. The problem continues for far longer than a launch from Earth. A chemical rocket burns for minutes. An interstellar propulsion system may need to operate for months or years, depending on thrust. Valves must cycle repeatedly. Pumps must move propellant without seizing. Engine surfaces must endure radiation, vibration, and extreme temperature without developing cracks that grow with every load. A tiny defect can remain invisible at first. Then it lengthens, then the next burn begins. This is material fatigue. Bend a paperclip once and it survives. Bend it again, and a crack forms where the metal appears strongest. An interstellar engine cannot be replaced as easily as a paperclip, especially when its failure throws the entire ship off balance. Fuel creates another trap. A conventional rocket must accelerate not only its crew and habitat, but also the propellant intended for later burns. More propellant adds mass. Added mass demands still more propellant. The cycle resembles packing water for a desert crossing. Then discovering that carrying the extra water makes the vehicle consume more fuel, which must also be carried. No ordinary chemical rocket can provide a practical answer at 1/10 of light speed. Its exhaust velocity is far too low. Concepts involving fusion, antimatter, or externally driven sails may offer much greater performance, but none has propelled a crewed starship. Each moves the danger rather than erasing it. A fusion engine needs reactions controlled with extraordinary reliability. Antimatter would require production and storage on a scale far beyond present capability, with catastrophic consequences if containment failed. A laser-driven sail shifts much of the energy source away from the ship, but demands a colossal beam, precise aiming, and a credible way to slow at the destination. Whatever system is chosen, inefficiency becomes heat on Earth. Engines can transfer heat into air, water, or surrounding ground. Space offers no atmosphere to carry it away. Heat can move through the vessel by conduction and circulating fluid, but it can leave only as radiation. That requires radiators. Large ones, they behave less like car radiators and more like glowing surfaces aimed into darkness. Their temperature and area determine how quickly energy escapes. If an engine produces more waste heat than the radiators can emit, the spacecraft warms even when every component is operating exactly as designed. Think of a busy kitchen sealed without windows, fans, or air conditioning. Every burner adds heat. Turning on more burners cooks dinner faster, but the room soon becomes unbearable. On the ship, reducing thrust may protect the machinery, yet it extends acceleration and changes the entire schedule. Radiators also create structural vulnerability. They must expose wide surfaces to cold space. A coolant leak may begin as a minor puncture and end by forcing an engine shutdown. That failure does not have to explode to become deadly. Suppose cooling performance falls gradually. The control system reduces engine power. Acceleration lasts longer. Fuel margins shrink. The planned turning point arrives late. The ship still appears healthy, but it may no longer possess enough propellant or functioning engine life to brake at Proxima. Detection, therefore, matters as much as strength. Temperature sensors need independent designs. Coolant loops need isolation valves. Thrust must be measured from several locations. A single computer should never be allowed to mistake a warped structure for a navigation error and command an even more damaging correction. Then comes deceleration. Reaching cruise speed is only half the propulsion problem. Unless the destination provides a tested external braking method, the ship must carry the means to cancel its forward motion. It may turn around and fire its engines in the opposite direction. It may deploy a magnetic sail against charged particles. It may use a beam sent from afar. Every option demands hardware that must function after decades of dormancy, radiation exposure, and microscopic wear. An engine that works perfectly near Earth can still betray the crew 40 years later. This changes the risk ranking. Propulsion can end the mission early and violently. Heat can disable it quietly. Both can be detected, monitored, and given redundant paths, but neither offers easy recovery after the main braking system is lost. They decide whether the voyage is physically possible, yet they are not automatically the first killers. A failed launch burn may strand the ship where rescue remains conceivable. A late braking failure may leave everyone alive aboard a vessel that can never stop. And solving that problem by choosing a higher cruise speed creates a new one. At ordinary speeds, a grain smaller than sand is dirt. At interstellar speed, it is ammunition. A collision at interstellar speed does not resemble a stone striking a windshield. The projectile barely has time to remain matter. At 20% of light speed, a dust particle weighing 1 milligram carries about 1.8 billion joules of energy. That is equivalent to more than 400 kilograms of TNT, concentrated into something smaller than a grain of sand. Our reference ship travels at half that speed. The energy released by the same particle would be lower, but still close to 108 kilograms of TNT. The spacecraft would spend more than 4 decades sweeping through everything lying across a path, 4.25 light-years long. Interstellar space is thin. It is not perfectly empty. Most of its matter is gas. Hydrogen and helium atoms are too small to punch holes like bullets. Yet the ship meets them at 30,000 kilometers per second. At that velocity, atoms strike the forward surface as energetic particles. They ionize material, break chemical bonds, implant themselves beneath the surface, and alter its structure. This is the first layer of danger. It is continuous rather than dramatic. A single atom accomplishes almost nothing. An enormous stream can heat exposed surfaces, damage optical instruments, disturb electronics, and slowly erode the material facing forward. The second layer is fine dust. These particles are less common than gas atoms, but each carries far more mass. On impact, the particle and part of the shield can flash into plasma. A tiny region becomes extremely hot, material melts, vaporizes, and sprays away. What remains may be a crater far larger than the original grain. One impact may be manageable. Millions of smaller impacts can remove material layer by layer. A published study examining small spacecraft moving near 20% of light speed, estimated that interstellar gas could damage approximately 1/10 of a millimeter of quartz. While this might erode around half a millimeter over part of the journey, those results reveal the physical mechanisms. They do not tell us how a massive crewed ship would perform. Its shape, speed, shield material, magnetic environment, path, and frontal area would differ. Most importantly, the distribution of interstellar dust is not mapped particle by particle along the route to Proxima Centauri. That uncertainty creates the third layer. Larger grains should be rare, but rare is not impossible when the spacecraft presents a broad target for decades. A particle only a few times heavier than the example above can release several times more energy. At these speeds, there is no time for a mechanical plate to bend gently and spread the load. The front layer becomes a rapidly expanding cloud of plasma and fragments. If the hull consists of one thick wall, that cloud may drive damage deeper into the ship. A better defense uses distance as well as mass. The first layer is sacrificial. It is intended to break the incoming particle apart. A gap follows. During the crossing of that gap, the debris cloud expands. Later layers then absorb a wider, less concentrated impact. This principle resembles a Whipple shield, although an interstellar version would face energies far beyond those encountered by satellites. Carbon-rich materials may be useful because they tolerate high temperatures and offer favorable strength for their mass. Other layers may include ceramics, foams, water, or replaceable panels. No single material solves every part of the problem. A layer good at resisting heat may create dangerous fragments. A strong metal may add too much mass. Water can absorb energy and serve other functions, but a punctured reservoir can also threaten life's support. The shield must therefore be treated as a system, not a wall. Sensors could measure impacts and map erosion. Robots could inspect the forward face without exposing people. Replaceable tiles could be moved from protected storage. The ship might carry raw material and manufacture new sacrificial panels during the voyage. But repairs at the bow would be difficult. The damaged area points directly into the incoming stream. Turning the vessel for maintenance could expose radiators, habitats, or engines that were never designed to face forward. Even a short maneuver would need careful timing and temporary protection. Detection offers another possible defense. Radar or laser systems might identify larger objects ahead. If the warning arrives early enough, the ship could make a small course correction or send material forward to disperse the threat. Yet a tiny dark particle is an exceptionally difficult target. At nearly 30,000 kilometers per second, an object detected 1,000 kilometers away would reach the ship in only a fraction of a second. The sensors must see farther, process faster, and operate after years of erosion. They must also distinguish real particles from noise without ordering constant evasive maneuvers that waste propellant. Some concepts place a cloud of dust, liquid droplets, or thin protective objects far ahead of the spacecraft. Incoming grains collide with this expendable screen before reaching the main hull. The idea can reduce concentrated impacts, but maintaining a stable shield across billions of kilometers introduces its own navigation problem. The screen must remain aligned while the ship accelerates, turns, and brakes. So is dust the most likely first killer? Not necessarily. At 10% of light speed, serious protection may be possible if the route is measured. The frontal area is minimized, and damaged layers can be renewed. At 20%, every impact carries about 4 times as much energy in the non-relativistic approximation. A design that survives the slower mission may fail at the faster one. The honest answer depends on information. Humanity does not yet possess the true population of larger grains, the behavior of full-scale shields, and the reliability of repair systems across decades. More shielding reduces this danger, but mass makes propulsion harder, and when fast particles strike that shielding, the collision can produce secondary fragments, neutrons, and other radiation immediately beside the crew. A thicker wall may stop the dust. It may also create the next threat inside itself. During Curiosity's flight to Mars, its radiation detector measured an average dose of about 1.8 millisieverts per day. That voyage lasted roughly 8 months. This one approaches half a century. The comparison is disturbing, but it must be handled carefully. Multiplying that daily measurement by 50 years would not produce a reliable prediction of illness or death. Curiosity traveled inside a particular spacecraft, through a particular period of solar activity, with shielding unlike anything designed for an interstellar vessel. The measurement gives us scale. It does not give us a verdict. Radiation in deep space also refuses to behave like one uniform substance. Some arrives from the sun. Solar energetic particle events can flood space with fast protons after powerful eruptions. These storms are irregular. Warning may be short, but their intensity can rise dramatically. A well-protected refuge can reduce the dose if the crew reaches it quickly. The harder problem comes from beyond the solar system. Galactic cosmic rays are atomic nuclei accelerated to enormous energies by events across the galaxy. Many are protons. Some are helium nuclei. A smaller fraction consists of heavy ions, including carbon, oxygen, silicon, and iron. Their numbers are lower, yet their biological effect can be severe because they deposit energy along dense, narrow tracks. An X-ray can damage DNA through relatively scattered interactions. A heavy ion can pass through a cell like a microscopic wrecking line, leaving clusters of broken molecular bonds close together. It may cut both strands of DNA, damage nearby proteins, and disturb several cellular structures along one path. The cell may die. It may repair itself incorrectly, or it may survive with changes that contribute to cancer years later. This is why absorbed dose alone cannot describe the danger. One gray from different radiation types does not always cause equal biological injury. Decades of human evidence for energetic ions do not exist. The damage would not be limited to cancer. Radiation can affect the lens of the eye, increasing cataract risk. It may injure blood vessels and raise concern about cardiovascular disease. Large acute doses can suppress bone marrow, reducing the body's ability to make blood cells and fight infection. Researchers also study possible effects on the brain, including changes in memory, attention, and decision-making. That last risk matters immediately aboard a starship. A small decline in judgment does not remain a private medical problem when the affected person maintains the oxygen system or commands an emergency maneuver. The spacecraft therefore needs shielding. But adding metal is not the simple answer it appears to be. When a high-energy cosmic ray strikes an aluminum wall, it can collide with a nucleus inside the material. The original particle may break apart. The aluminum nucleus may also fragment. Neutrons, protons, lighter nuclei, and other secondary particles can then continue into the vessel. The wall stopped the primary particle. It also created a spray. This process is called nuclear fragmentation. It explains why a shield cannot be judged only by whether an incoming particle penetrates its full thickness. Engineers must calculate what emerges from the inner side, where that radiation travels, and how much biological damage it can cause. Imagine a helmet that stops a heavy object, but transfers much of the impact into the skull. The outside remains unbroken, yet the person inside is still injured. Radiation shielding must control both the original strike and the consequences produced inside the protective material. Hydrogen-rich substances often perform better per unit of mass than heavy metals against many components of space radiation. Hydrogen nuclei are light, so collisions tend to produce less destructive fragmentation than impacts involving heavier nuclei. Polyethylene contains large amounts of hydrogen. Water does too. That creates an opportunity. The ship already needs water, food, plastics, and waste processing materials. These supplies can surround occupied spaces instead of sitting wherever they fit. A central storm shelter could lie between water reservoirs and blocks of hydrogen-rich material. During a solar event, the crew could shelter there together and sharply reduce exposure. Yet even this design has limits. Water is consumed, purified, and redistributed. A complete shield at departure may gradually develop thin regions later. Food disappears, pipes create gaps, and doors interrupt protection. Radiation does not need a dramatic hole. It needs an easier path. Dosimeters must therefore be distributed across the vessel. Personal sensors can record each crew member's exposure. Fixed detectors can map changes from one compartment to another. Different instruments should identify particle type and energy, because one average reading may conceal a dangerous shift in radiation quality. The crew needs operational rules. Sleeping quarters can occupy protected zones. After a solar warning, non-essential work must stop so everyone reaches shelter. Medical records must track exposure and neurological changes. Even with all these measures, radiation cannot be reduced to zero. More shielding adds mass, more mass increases propulsion energy. Certain materials reduce one particle field while increasing another. Every design becomes a compromise between dose, weight, geometry, repairability, and the supplies required for 50 years. NASA currently groups radiation, isolation, distance, altered gravity, and closed environments among the major hazards of human spaceflight. On this mission, weakening one system can amplify failures elsewhere aboard. So, radiation is a serious candidate for causing the first death. But it is difficult to rank by a calendar. Its pressure accumulates unevenly. A solar storm may produce a sudden crisis. Galactic cosmic rays may raise risk quietly for years. Individual biology will differ, and the shield itself will change as the ship ages. Still, the crew cannot spend 50 years motionless inside a shelter. Their bodies need another form of protection, one that no wall can provide. Without gravity, bones release minerals, muscles weaken, fluids shift toward the head, and the cardiovascular system adapts to a world with no permanent down. The proposed solution is to make part of the ship rotate. But once the floor begins moving, gravity returns with conditions. No human has ever lived for years inside a rotating spacecraft. That fact separates artificial gravity from nearly every familiar technology aboard this proposed mission. Engineers understand rotation, doctors understand many effects of weightlessness. But humanity has never combined the two in a habitat and watched a large crew age inside it for decades. The physics is not mysterious. When a habitat rotates, its floor continually pushes people inward, forcing their bodies to follow a circular path. To someone standing inside, that contact feels like weight pressing toward the floor. The ship has not created gravity. It has created acceleration that can imitate part of gravity's effect. How convincing that imitation feels depends mainly on two things: the radius of the habitat and its rotation rate. A large ring can turn slowly while producing a comfortable downward force. A small ring must spin faster to create the same effect. Faster rotation saves structure and perhaps mass, but it makes human movement more complicated. Stand still, and the floor may feel normal. Turn your head, climb a ladder, or walk toward the center, and the sensation can change. This happens because motion inside a rotating environment produces Coriolis effects. A person moving across the ring changes speed relative to different parts of the habitat. The result can feel like an unexpected sideways push. The eyes report one direction of movement, while the balance organs in the inner ear report another. Nausea, dizziness, disorientation, and loss of coordination can follow. The experience is similar to trying to walk straight across a spinning amusement park platform. Your feet, head, and destination do not share the same direction or speed. After training, many people adapt. But adaptation measured over days is not proof of health over 50 years. Children might develop aboard such a vessel. Injured crew members might spend months in bed. Older adults could become more sensitive to imbalance. A rotation rate tolerated by a healthy 30-year-old engineer may not be equally safe for a pregnant woman, a recovering patient, or a person in their 70s. The force may also vary from head to foot. In a small, rotating habitat, a person's feet are farther from the axis than the head. The feet, therefore, experience stronger artificial gravity. Blood, bones, muscles, and the balance system receive a gradient that does not exist in the same way on Earth. A larger radius reduces that difference, which is another reason size matters. But a larger ring is not free. It needs more structural material. Its mass must be accelerated, protected from dust, supplied with air, and connected to the rest of the spacecraft. If it rotates around a stationary central section, bearings or magnetic supports must manage the interface. Power, water, data, and ventilation must cross between moving and non-moving structures without creating fragile single points of failure. Even a tiny imbalance can become important. People move, water shifts between tanks, food is consumed, machinery is relocated, waste accumulates. If mass gathers unevenly around the ring, the rotating structure can wobble. Control systems must redistribute loads or apply corrective forces. Otherwise, the same small vibration can repeat millions of times. Repetition is how harmless motion becomes fatigue. A bearing may survive 100 rotations without measurable damage. During a mission lasting 5 decades, the habitat may complete hundreds of millions of rotations. Depending on its speed, microscopic defects can grow, lubricants can degrade, seals can harden, sensors can drift. A component designed with an impressive service life on Earth may still fail when no factory can replace it. Stopping the ring for repairs creates a medical problem immediately. The crew would not float harmlessly and continue as usual. Loose objects could shift. Fluids would redistribute within human bodies. People adapted to artificial gravity could experience sickness and loss of coordination. Work in the stopped habitat would become slower just when technicians need precision. Restarting introduces another load cycle. Every compartment must accelerate together. Tanks need internal controls to prevent liquid from sloshing dangerously. Furniture, farms, medical equipment, and sleeping quarters must withstand forces that change direction during spin-up and spin-down. Designers could avoid mechanical bearings by rotating the entire spacecraft. That removes one difficult interface, but creates others. Antennas must maintain communication while turning. Telescopes and navigation sensors need stable sightlines. Radiators may receive changing exposure. Engines must apply thrust through a rotating structure without exciting destructive oscillations. There is also an unanswered biological question: how much gravity is enough? Mars provides about 38% of Earth's surface gravity. The Moon provides about 16%. Humans have walked in both environments, but nobody has lived for years under either level. We do not know the minimum continuous force that reliably preserves bone, muscle, vision, cardiovascular function, pregnancy, and childhood development across decades. Exercise will still matter. Resistance machines and aerobic training can slow physical decline, as experience aboard the International Space Station has shown, but exercise consumes crew time, equipment life, power, and medical supervision. It is a countermeasure, not a complete substitute for a known gravitational environment. Artificial gravity, therefore, occupies an unusual place in the risk ranking. It is not the most likely sudden killer. A person does not usually die because a ring slows slightly. The danger arrives through reduced strength, a poor balance, cardiovascular changes, injury, and diminished ability to perform repairs. Then a fire, pressure leak, or medical emergency occurs, and a weakened crew must respond. The same pattern now appears across the first 5 suspects. Propulsion and heat determine whether the ship can depart and stop. Gas and dust determine whether its forward defenses survive the crossing. Radiation and gravity determine whether the people remain healthy enough to operate everything else. None can be ignored. None can yet be declared the certain cause of the first death. But the external universe may not need to breach the hull at all. The earliest fatal chain could already be quietly circulating through every breath, every cup of water, and every meal. Inside a sealed spacecraft, oxygen is only one part of the breathing problem. Carbon dioxide may become dangerous long before the crew feels that the air is running out. Every person continually takes oxygen from the cabin and returns carbon dioxide, water vapor, heat, and trace chemicals. On Earth, the atmosphere dilutes those products. Plants, oceans, weather, and enormous volumes of air help redistribute them. Inside a starship, every exhaled molecule remains aboard until machinery or biology moves it somewhere else. For 100 people, breathing never pauses without interruption aboard. A resting adult may produce roughly 1 kilogram of carbon dioxide per day, with output rising during exercise and heavy work. Across the crew, that approaches 100 kilograms every 24 hours. A removal system that falls behind by only a small percentage can allow the gas to accumulate. Even though fans are turning and oxygen measurements still appear normal, that distinction is critical. Adding oxygen does not remove carbon dioxide. A room can contain enough oxygen, while carbon dioxide climbs to levels that cause headache, fatigue, poor concentration, faster breathing, and impaired judgment. At higher concentrations, confusion and loss of consciousness can follow. The first signs may resemble stress, lack of sleep, infection, or motion sickness. By the time several people recognize the same pattern, the system may already be losing control. Spacecraft use absorbent materials to capture carbon dioxide from circulating air. On the International Space Station, equipment such as the carbon dioxide removal assembly passes cabin air through beds containing zeolite. The material selectively traps carbon dioxide. Heating and pressure changes then release the captured gas so the bed can be used again. Two beds can alternate. One collects while the other regenerates. That sounds continuous, but it depends on valves, heaters, fans, seals, sensors, software, and clean airflow. Dust can obstruct passages, moisture can reduce performance. A valve can stick. An inaccurate sensor can tell the controller that a bed has regenerated when it has not. On a station near Earth, specialists can study telemetry, rewrite procedures, and prepare replacement hardware. The Interstellar crew must do all of that themselves while continuing to breathe the air controlled by the failing machine. Cabin averages can also hide local danger. Carbon dioxide does not instantly mix throughout a large vessel. Fans create circulation, but racks, sleeping compartments, storage areas, and rotating sections produce pockets of slower airflow. A sensor in the central passage may report an acceptable reading, while gas accumulates near a person's face during sleep. This has practical consequences. The ship needs sensors in many compartments, not one trusted number. Airflow must be mapped after furniture moves, farms expand, or ventilation ducts are repaired. Personal monitors may be necessary during maintenance in confined spaces. Crew members must understand that a normal oxygen reading does not prove the atmosphere is safe. Then comes oxygen recovery. Water can be split by electrolysis into oxygen and hydrogen. The oxygen returns to the cabin. The hydrogen can react with captured carbon dioxide in a Sabatier system, producing water and methane. Recovering that water closes part of the loop and reduces the amount that must be stored. But the loop is not perfect. Methane contains carbon and hydrogen that may leave the useful cycle unless another process recovers them. Small leaks remove oxygen and nitrogen from the cabin. Air escapes whenever a compartment is vented or a seal fails. Filters and chemical beds eventually become contaminated. Over 5 decades, losses that appear trivial during a 1-year mission become large inventories. The ship therefore needs reserve gases, replaceable absorbents, repairable machinery, and more than one chemical pathway. Redundancy cannot mean placing 2 identical units beside each other if both share the same software, coolant line, or flawed valve design. One hidden defect could disable both. True resilience requires separation, independent sensors, different control logic, manual sampling methods, emergency chemical canisters that work without the main power network. Fire makes atmospheric control even harder. Combustion consumes oxygen and produces carbon dioxide, carbon monoxide, smoke particles, and toxic compounds from plastics. After flames are extinguished, the air may remain dangerous. Filters must remove microscopic particles. Catalytic systems must process carbon monoxide and volatile chemicals. Contaminated compartments may need isolation, reducing the habitable volume available to the crew. Plants can help, but they cannot be treated as a magical backup. In light, crops consume carbon dioxide and release oxygen through photosynthesis. In darkness, they continue to respire, consuming oxygen and releasing carbon dioxide. Their performance changes with temperature, disease, nutrient supply, leaf area, and lighting. If the electrical system fails, the farm can shift from a major oxygen source to another oxygen consumer. A biological loop also responds slowly, compared with an emergency scrubber. Crops cannot instantly increase photosynthesis because a valve failed during the night. Machinery remains essential, even on a ship built around agriculture. The most dangerous atmospheric failure may therefore begin as a mismatch, not a total shutdown. Carbon dioxide production exceeds removal by a few kilograms each day. A sensor drifts low. The crew compensates by opening another habitat section, increasing the air volume but masking the trend. Technicians work longer hours, producing more carbon dioxide while fatigue makes diagnosis less reliable. Nothing dramatic happens at first. That is precisely why the chain can grow. Life support must be judged by survival margin, the distance between what the crew produces and what the ship can safely process. Equipment designed to handle exactly 100 people has no real margin for exercise, fire, illness, maintenance, or declining efficiency. Capacity must exceed normal demand, even after one major unit is offline. Air places life support near the top of the risk ranking because failure can harm everyone and recovery time can be short. Yet air recycling does not operate alone. Its electrolysis cells need purified water. Its scrubbers need cooling. Its crew needs enough water to remain healthy and capable of repair. And aboard this ship, yesterday's wastewater must become tomorrow's drink. 100 people can consume and use several hundred liters of water every day. They drink it. They prepare food with it. They wash. They produce it in urine, sweat, breath, and waste. The ship can carry a large reserve, but it cannot carry 50 years of fresh water, as if every used liter will be thrown away. Water must circulate. A modern spacecraft can recover water from humidity and urine, then process it until it is safe for human use. Recent improvements aboard the International Space Station have demonstrated recovery approaching 98% when water extracted from urine brine is included. For an interstellar mission, it is also incomplete. If a system permanently loses 2% of its water on every pass through a simple cycle, the supply would collapse quickly. Real mission accounting is more complicated because not all water enters the same loop at the same time, and reserves can replace losses. But the central lesson remains a small unrecovered fraction, becomes enormous when multiplied across 100 people and nearly 5 decades. Suppose total human and operational use average only 300 liters per day. A 2% net loss would equal 6 liters daily. Over 50 years, that would exceed 100,000 liters before leaks, repairs, farming, firefighting, or medical use were added. So 98% cannot be the final design target for the entire ship. Water begins its return in several forms. Humidity condenses from cabin air. Sweat evaporates from skin. Moisture leaves every breath. Dehumidifiers collect it, protecting electronics and preventing mold while feeding the recycling system. It contains water mixed with salts, organic compounds, medications, hormones, and metabolic waste. A distillation assembly can separate much of the water, often using reduced pressure, so boiling occurs at a lower temperature. The remaining liquid becomes concentrated brine. Recovering more water from that brine requires additional equipment, such as membranes and air evaporation. Without allowing contaminants to cross into the product stream, the recovered liquid is not ready to drink merely because it looks clear. It passes through filters and treatment beds that remove particles, dissolved chemicals, and microorganisms. Catalytic oxidation can break down remaining organic contaminants. Sensors test conductivity, organic content, and other indicators. Disinfectants help prevent bacteria from multiplying inside storage tanks and pipes. Each stage protects the next. Each stage can also fail differently. A torn membrane may allow contamination through. A saturated filter may stop capturing chemicals. A heater may run cool. A sensor may remain within its electrical limits while its reading slowly drifts away from reality. Microbes can attach to wet surfaces and form biofilms, slimy communities that resist disinfectants and narrow pipes. Biofilms are more than a cleanliness problem. They can corrode material, obstruct valves, alter sensor readings, and shelter organisms that later break free into the water supply. Some microbes may adapt to the closed environment. Others may exchange genes. The ship must monitor not only whether organisms are present, but where they are growing and how their population changes over years. If a monitor reports contamination, is the water unsafe, or is the monitor faulty? Drinking it could poison the crew. Discarding it could destroy a limited reserve. Waiting for certainty may consume the time needed to prevent illness. The system, therefore, needs separate storage zones. Newly recovered water should not immediately mix with the entire clean supply. Suspect batches can remain isolated until multiple tests agree. Tanks must be small enough to quarantine, yet large enough to support the crew during repairs. Water storage can perform several jobs. Tanks placed around sleeping areas add radiation shielding. Thermal loops move heat from equipment to radiators. Farms use water as both a biological resource and a carrier for nutrients. Fire suppression depends on an emergency supply. That efficiency is attractive, but it creates coupling. A leak in a shield tank becomes a drinking water loss. Contamination in an agricultural loop may threaten food and water together. A cooling failure may force engineers to sacrifice clean water to protect machinery. The same leader cannot safely perform every role at once without valves, barriers, and verified treatment between uses. Maintenance introduces further losses. Pipes must sometimes be drained before repair. Filters retain moisture when removed. Samples consume small amounts. Airlocks vent water vapor. Plants lock water inside growing tissue. Human bodies hold their share. Every location becomes part of the total inventory. Even when that water is temporarily unavailable, the crew needs a complete water map. Meters must record flow into and out of every major process. Tank levels need independent measurement methods. Unexpected differences must trigger investigation before a hidden leak spreads behind a wall. A loss of 1 liter per day can appear harmless, yet over 10 years, it becomes more than 3,600 liters. Reserve capacity determines whether the crew can recover from such events. If the main processor stops, stored water must last longer than the repair. If contamination forces a section offline, another treatment route must carry essential demand. Emergency rationing can reduce washing and some farm use, but people still need water for drinking, food preparation, medicine, and sanitation. Dehydration quickly reduces mental and physical performance. Severe gastrointestinal infection can increase water demand, exactly when contamination has reduced supply. Medical treatment may require clean water, while sick technicians leave fewer people available to repair the system. This is how a water problem becomes a crew problem, then an air problem, then a maintenance problem. The loop survives only if detection, isolation, repair, and reserves work together. High recovery efficiency reduces launch mass. It does not guarantee safety. The real standard is whether the ship can continue supplying clean water while its best processor is broken and part of its inventory is unusable. Water may circulate almost perfectly and still leave another limit untouched. It carries nutrients to crops, supports metabolism, and keeps people alive. But it contains no calories, essential amino acids, or vitamins. A full tank cannot feed the crew. A human body cannot store 50 years of nutrition. Neither can an ordinary warehouse. 100 adults consuming an average of 2,000 calories per day would require more than 73 million calories every year. Across a mission lasting approximately 5 decades, total demand would exceed 3.6 billion calories. That calculation includes only basic energy. It does not include spoiled food, agricultural losses, emergency reserves, pregnancy, childhood growth, heavy physical work, illness, or the different metabolic needs of individual crew members. The ship must therefore produce a substantial portion of its food continuously. Stored meals provide a valuable buffer. They are predictable. They require no growing season, pollination, or disease control. But food does not remain nutritionally unchanged simply because the package stays sealed. Fats can oxidize, flavors deteriorate, textures change. Some vitamins slowly break down. Vitamin C, thiamine, folate, and several other micronutrients may decline during long storage, depending on temperature, oxygen exposure, radiation, moisture, and packaging. Freezing can slow many reactions, but refrigeration demands power and working machinery. Shielding food from radiation adds mass. No preservation method has been demonstrated for a complete human diet stored safely across 50 years in deep space. A package may still contain calories while no longer providing the nutrition printed on its label. That distinction could take years to become visible. A crew member does not collapse the first day vitamin intake falls. Deficiencies develop gradually. Fatigue appears, wounds heal more slowly. Immunity weakens. Vision, nerves, bones, or blood production may suffer, depending on the missing nutrient. Those symptoms can resemble radiation effects, infection, depression, overwork, or aging. The farm is intended to prevent that decline. Plants convert light, carbon dioxide, water, and nutrients into edible tissue. They also release oxygen while illuminated and remove part of the carbon dioxide produced by the crew. In principle, agriculture can connect food production with atmospheric control and waste recycling. In practice, every connection creates another path for failure. Crops require light at the correct intensity and wavelength. Electric lamps convert power into usable radiation, but much of the energy becomes heat. Cooling equipment must remove that heat. Pumps must deliver water and nutrients to roots. Sensors must track acidity, salinity, humidity, temperature, and carbon dioxide. If electricity falls, the farm does not merely become dark. Photosynthesis slows. Food production drops. Oxygen generation declines. Plants continue respiring. Humidity changes. Heat and carbon dioxide begin moving through the habitat differently. The agricultural system may shift from supporting life to increasing the burden on life support. Growing enough food also demands area. Highly productive crops can provide large amounts of edible material per square meter. But one crop cannot provide a balanced diet. Wheat and potatoes offer calories. Soybeans can supply protein and fat. Leafy vegetables contribute vitamins and minerals. Fruits improve variety and provide additional nutrients. Yet they often require more time, space, or labor. The crew needs diversity for biological reasons, not luxury. A farm dominated by one efficient species is vulnerable to a single pathogen. A genetically uniform crop population may respond to disease in nearly the same way. If one plant lacks resistance, thousands may share that weakness. On Earth, farmers can obtain new seeds, pesticides, equipment, and expert assistance. The starship cannot. Fungi may spread through humid growing chambers. Bacteria can colonize nutrient lines. Insects or mites accidentally carried aboard may reproduce without natural predators. A virus infecting plants could remain unnoticed until leaves deform and yields fall. The crew cannot simply spray every outbreak with powerful chemicals. Residues may enter recycled water or cabin air. A treatment that kills a fungus may damage beneficial microbes needed for waste processing. Burning infected plants would consume oxygen and produce contaminants. Agricultural compartments, therefore, need isolation. Air should not move freely from every farm into every other farm. Nutrient solutions must be separable. Seed stocks should remain protected in the multiple locations. Different crop varieties need enough genetic diversity to prevent one disease from destroying an entire category of food. The crew must also preserve knowledge. Agriculture aboard the ship will not behave exactly like farming on Earth. Artificial gravity may alter root orientation and water movement. Plants may experience elevated radiation. Pollination may require controlled airflow, insects, or human assistance. Microbial communities around roots could change over generations. Farmers will need to observe, experiment, and adapt. That requires trained people. If only 3 crew members understand the complete agricultural system, an accident or illness affecting them becomes a food emergency. Procedures can be recorded, but written instructions do not replace years of practical judgment. A manual may explain how to adjust nutrient concentration. It cannot instantly teach someone to recognize the smell, color, or growth pattern that signals an early disease. Skills must be distributed across generations. Children born during the voyage may become the technicians, physicians, and farmers who complete it. Education is therefore part of life support. The ship must preserve scientific understanding, while giving younger crew members real experience before older experts retire or die. Food processing creates another dependency. Harvested wheat is not immediately bred. Soybeans require preparation. Plant material must be cleaned, stored, milled, cooked, and distributed. Kitchens need energy, refrigerators need cooling, surfaces must remain sanitary. Waste must return nutrients to agriculture without returning dangerous pathogens. Human waste contains nitrogen, phosphorus, potassium, and other useful elements. Throwing those materials away would slowly empty the farm's nutrient inventory. Yet untreated waste may contain bacteria, viruses, parasites, medications, and chemical residues. Recycling requires controlled biological and chemical processing. Some nitrogen can be recovered and converted into forms plants absorb. Phosphorus must be captured before it accumulates in inaccessible deposits or leaves the useful loop. Trace elements such as iron, zinc, copper, and selenium must remain available in suitable amounts. Too little creates deficiency. Too much becomes toxic. No recycling loop is completely closed. Nutrients become trapped in filters, damaged equipment, inedible plant tissue, or human remains. Small losses accumulate. The ship must carry concentrated reserves and possess instruments capable of detecting shortages before harvests decline. then there is appetite. Eating the same flavors for decades can reduce food intake even when nutritional calculations appear adequate. Stress, altered smell, medication, illness, and isolation may further suppress appetite. Meals also provide routine, culture, and social connection, on a voyage with no natural seasons and no changing landscape. Food may become one of the strongest remaining links to ordinary human life. A technically complete diet that people refuse to eat is not complete. The safest architecture combines stored food, continuous agriculture, protected seeds, nutrient reserves, microbial protein, and emergency rations. These layers must fail independently. A power interruption should not destroy every crop. A disease outbreak should not contaminate all seed banks. A poor harvest should not force immediate starvation. Food failure would probably begin quietly. One crop produces less than expected. Stored vitamins have degraded faster than predicted. A nutrient sensor reads slightly high. The farm manager reduces supplementation. Months later, several crew members develop fatigue and poor wound healing. No single event looks fatal. Together, they weaken the people responsible for restoring the system. Calories can keep a person alive, while nutritional imbalance makes that person less capable of protecting everyone else. And when weakened immunity meets a closed population, a problem that began in the farm can quickly arrive in the clinic. A hospital on Earth survives because it is connected to an entire civilization. Blood banks deliver matched units. Laboratories identify pathogens. Pharmacies replace expired drugs. Specialists examine unusual scans. Manufacturers supply sterile instruments, implants, oxygen, reagents, and disposable equipment. The clinic aboard the Starship has none of those networks. It must serve 100 people for approximately 50 years, using only what departed with them, what they can manufacture, and what their descendants can learn. The first medical emergency could be ordinary. A crew member slips during maintenance and suffers internal bleeding. Another develops appendicitis. A tooth becomes infected. A cut introduces bacteria into tissue. A pregnancy becomes complicated. A blood clot blocks an artery. None requires an exotic space disease. They require time, diagnosis, trained hands, sterile equipment, and the correct treatment. Limited population size makes medical planning difficult. Many conditions will be rare across 100 people. Yet almost any rare condition can occur during 5 decades. Carrying dedicated equipment for every possibility would consume enormous mass and storage volume. Leaving it behind turns probability into vulnerability. The clinic needs broad capability rather than a separate machine for every disease. Ultrasound can examine organs, guide needles, monitor pregnancy, and reveal internal fluid without exposing patients to ionizing radiation. Compact laboratory systems can analyze blood, urine, and microbial samples. Three-dimensional printers may produce selected tools or components, but versatile equipment still requires consumables. A diagnostic cartridge performs only a limited number of tests. Sterile gloves tear, adhesives age, batteries degrade, chemical reagents lose reliability, plastic tubing becomes brittle. Even instruments designed for reuse must be cleaned, sterilized, inspected, and repaired. Medicine itself has a lifespan. Expiration dates do not mean every drug becomes dangerous immediately afterward. Many medications retain useful potency beyond their labeled period when stored correctly. But stability differs between compounds. Heat, radiation, moisture, and packaging can accelerate degradation. Liquid drugs and biological products may be especially difficult to preserve for decades. The crew may be able to manufacture some simple medicines from stored chemical precursors. Producing complex antibiotics, hormones, vaccines, antibodies, or anesthetic agents is much harder. It requires controlled reactions, purification, testing, and confirmation that the final product has the correct identity, concentration, and sterility. A contaminated medicine can be worse than no medicine. Antibiotics create a deeper problem. Bacteria live on every person and throughout the ship. Most are harmless or beneficial. In a closed environment, however, the same microbial populations encounter disinfectants, medications, metal surfaces, recycled water, and repeated antibiotic use for generations. Selection never stops. When an antibiotic kills susceptible bacteria, organisms with protective traits may survive and multiply. Resistance genes can move between bacteria. A treatment that worked during the first decade may become less reliable during the fourth. The crew cannot request a newly developed drug from Earth. Strict infection control becomes essential. Antibiotics should be used only when evidence supports them. Microbial samples must be preserved so doctors can compare current organisms with earlier populations. Genome analysis may help identify pathogens and resistance genes, but genetic information alone does not always reveal which drug will work inside a living patient. Culture remains valuable. Doctors can expose bacteria to different medicines and observe which ones stop growth. That process requires sterile media, incubators, supplies, and time. A patient with rapidly spreading sepsis may not have time to wait. Sepsis begins when the body's response to infection damages its own tissues and organs. Blood pressure can fall. Clotting becomes abnormal. Kidneys, lungs, brain, and heart may begin failing. Treatment often requires intravenous fluids, antibiotics, oxygen, laboratory monitoring, and sometimes mechanical support. Each treatment draws from another system. Fluids consume purified water and sterile salts. Oxygen comes from life support. Temperature control depends on electrical and thermal systems. A ventilator needs power. Dialysis produces a heavy demand for water, filters, and trained supervision. The patient may survive the infection while the treatment places new pressure on the ship. Surgery is even more demanding. Artificial gravity would make fluids and instruments behave more normally than in weightlessness. But rotation introduces its own constraints. The operating room needs stable gravity, clean air, strong lighting, suction, anesthesia, imaging, sterilization, and backup power. If the rotating habitat must stop during a mechanical emergency, surgeons may suddenly face a medical procedure in microgravity. Blood no longer drains downward in the familiar way. Fluids can form floating droplets. Tools must be restrained. The patient must be secured. Airway management becomes harder when both equipment and staff move differently. Training cannot be limited to one environment, nor can it be limited to one physician. If the only surgeon is the patient, the title becomes meaningless. At least several crew members need overlapping skills in surgery: anesthesia, dentistry, obstetrics, critical care, infectious disease, mental health, and rehabilitation. No small crew can carry full specialists in every field. Artificial intelligence may assist diagnosis, retrieve procedures, interpret images, and guide less experienced clinicians. But software cannot replace missing instruments, manufacture blood, or guarantee that an unusual symptom matches its database. It may also inherit errors from training data or fail when sensors provide incomplete information. Human judgment remains necessary. So does blood. Whole blood and many blood products cannot simply be stored for 50 years. The crew itself becomes the renewable donor pool. Blood types must be mapped. Donors need screening. Collection and transfusion equipment must remain sterile. A large accident involving several people could rapidly exhaust compatible donors. A small population also increases genetic concerns. The mission must protect enough diversity for descendants, whether reproduction occurs naturally, through stored embryos, or with preserved reproductive cells. Pregnancy and childbirth introduce risks that cannot be eliminated by engineering. Hemorrhage, hypertension, infection, premature delivery, and fetal complications can arise even in excellent hospitals. Aboard the ship, one difficult birth may require surgeons, blood, medication, neonatal support, and several days of continuous care. Meanwhile, ordinary operations continue. Someone must maintain the atmosphere. Someone must watch the water system. Someone must protect the crops. Medical emergencies remove not only patients, but caregivers from the working crew. If 10 people are sick, perhaps another 10 are occupied treating them or performing their duties. A disease affecting a small fraction of the population can therefore disable a much larger fraction of the ship's operational capacity. Isolation can prevent transmission, but it also separates trained workers from critical systems. Ventilation paths need control. Shared surfaces require cleaning. Protective equipment must be available. The crew must distinguish contagious disease from radiation sickness, nutritional deficiency, chemical exposure, and carbon dioxide accumulation. Those conditions can initially look similar: headache, fatigue, nausea, confusion. A wrong diagnosis may send technicians to disinfect cabins, while a failing scrubber continues raising carbon dioxide throughout the vessel. This is why the clinic cannot function as a separate room, waiting for injured people. Medical monitoring must connect with environmental sensors, food records, radiation exposure, work schedules, and microbial surveillance. The first symptom may be the earliest warning of a mechanical failure. Medicine ranks high among the candidates for the first death, because human biology contains unavoidable uncertainty. Yet a fatal illness may not begin inside the patient. It may begin with contaminated water, missing nutrients, degraded medicine, weak staffing, or a sensor that persuaded everyone the environment was safe. The death certificate may name an infection. The investigation may reveal that the entire ship had already become the patient. No machine can measure how long a human being can endure a voyage with no possibility of escape. Astronauts have spent months aboard space stations. Researchers have lived in Antarctic bases through dark winters. Submarine crews have remained underwater for extended patrols. These experiences reveal how isolation affects sleep, mood, concentration, and relationships. None reproduces a journey to another star. Every person aboard the Proxima mission would know that Earth is becoming unreachable. During the early years, messages could still arrive from family and governments, but each response would take longer as distance increased. Near Proxima Centauri, a one-way radio signal would require more than 4 years. A question sent home might receive an answer nearly 9 years later. That is not a conversation. It is archaeology. The people who recorded a message may have changed, retired, or died before the reply arrives. Political systems may collapse. Mission agencies may disappear. Languages and cultural priorities may shift. The crew could continue receiving instructions from officials who no longer understand conditions aboard the ship. Eventually, authority must become local. That creates a psychological burden no earlier expedition has carried. The crew cannot abort the mission. They cannot request evacuation. They cannot vote to return home after the breaking point has passed. Even if everyone agrees that the voyage was a mistake, physics may leave them no alternative. A locked future changes human behavior. Some people may become deeply committed to the mission. Others may begin questioning why their lives must serve a destination chosen decades earlier. Children born aboard never agreed to leave Earth. They inherit a moving habitat, a limited population, assigned responsibilities, and a destination they have never seen. Their parents may call it humanity's greatest journey. They may call it confinement. Conflict does not require madness or evil. It can grow from ordinary disagreements about scarce resources. Should more electrical power support agricultural lighting or private living spaces? Should a sick crew member receive a treatment that consumes limited medicine? Should reproduction be delayed after a poor harvest? Who decides which repairs deserve the last reserve component? Every answer benefits someone and limits someone else. On Earth, dissatisfied people can change jobs, move to another city, form a new community, or appeal to outside institutions. Aboard the ship, the same 100 people share the same air, water, corridors, equipment, and danger. There is nowhere else to go. Privacy therefore becomes a life support resource. Crew members need spaces where they are not constantly observed. They need control over light, sound, communication, and social contact. Even a small private cabin can help preserve identity in a world where meals, exercise, work, and emergencies are communal. But volume is expensive. Every additional room increases hull mass, air demand, heating, cooling, wiring, maintenance, and shielding. Designers may be tempted to minimize private space because it does not appear essential on an engineering diagram. That saving could be costly. Crowding increases irritation and reduces the ability to recover after conflict. Repeated noise disrupts sleep. Lack of privacy can intensify stress. A person who cannot withdraw from an argument may carry that tension into the control room, clinic, or farm. Sleep loss deserves special attention. Artificial lighting must create a stable day and night cycle, without sunrise, weather, or seasons. Shift work will still be necessary because life support operates continuously. Alarms may interrupt rest. Machinery can produce constant vibration and low-frequency noise. Chronic sleep restriction reduces expansion, memory, reaction speed, and emotional control. A tired technician is more likely to overlook a valve position. A tired commander may interpret disagreement as disobedience. A tired doctor may choose the wrong dosage. Psychological stress becomes mechanical risk. The reverse is also true. A persistent coolant leak, declining harvest, or unexplained sensor alarm can keep the entire crew anxious for months. People may begin watching every reading for signs of catastrophe. Some may become overly cautious. Others may deny the danger because acknowledging it feels unbearable. Both responses can impair judgment. Depression may appear as exhaustion, social withdrawal, reduced motivation, or loss of concentration. Anxiety may produce rapid breathing, insomnia, irritability, and physical discomfort. These symptoms overlap with carbon dioxide exposure, infection, medication effects, radiation injury, and nutritional deficiency. The crew cannot assume every emotional change is psychological, nor can they assume every psychological problem has a mechanical cause. Monitoring must preserve dignity. Constant surveillance may detect declining performance, but it can also destroy trust. If crew members believe admitting distress will remove them from meaningful work or reproductive eligibility, they may conceal symptoms until a crisis develops. Confidential mental health care will be necessary. So will peer support, structured recreation, physical exercise, varied responsibilities, and contact with Earth for as long as communication remains meaningful. Virtual environments could provide forests, oceans, cities, and familiar homes. Recorded music, films, books, and family histories may protect cultural continuity. Simulation cannot replace freedom. A digital beach still ends at a metal wall. Leadership structure will matter most during disagreement. A military command system can make rapid decisions in emergencies, but decades of absolute authority may generate resentment or abuse. A democratic system provides legitimacy, yet prolonged debate can be dangerous during fire, decompression, or crop disease. The ship may need both. Emergency authority must be clearly defined, temporary, and reviewable. Ordinary governance needs transparent rules, independent medical judgment, conflict resolution, and a credible method for replacing leaders. No commander should control oxygen, discipline, reproduction, and access to information without oversight. The mission must also prepare for crime, theft, assault, sabotage, coercion, and domestic violence do not become impossible because the crew was carefully selected. Initial screening cannot predict behavior 30 years later, after bereavement, illness, family conflict, or political division. Traditional imprisonment would remove a worker from an already small population while consuming guarded space. Exile is impossible. Punishment cannot damage the person's ability to contribute to survival. Justice must protect victims without destroying the community it is intended to preserve. Generational change makes this harder. The first crew chose the mission and trained on Earth. The second generation grows inside it. By the third, Earth may feel like a story preserved in recordings. Younger people may challenge procedures treated as sacred by their elders. They may reject the destination, alter reproduction policies, or demand control of systems previously restricted to specialists. That conflict may be healthy. Blind obedience can preserve dangerous mistakes. Constant rebellion can destroy necessary discipline. A successful culture must teach people why procedures exist while allowing evidence to change them. Psychology is therefore not a separate category from survival. It influences maintenance, medicine, food production, leadership, education, and emergency response. A crew suffering from fear, mistrust, or exhaustion can turn a repairable failure into a fatal one. Yet human beings are also adaptable. They form families, rituals, humor, friendships, and new identities under difficult conditions. The same closed community that intensifies conflict can create extraordinary cooperation. Shared purpose may protect mental health when the mission feels meaningful and decisions feel fair. The danger begins when that trust erodes. A crew member may ignore an alarm because previous warnings were false. A technician may hide an error to avoid punishment. A faction may block access to equipment. A commander may suppress bad news to prevent panic. Then hardware that could have been repaired remains damaged. And after decades in flight, every neglected machine will be older than the people depending on it. A 50-year mission demands machinery that can survive longer than most modern careers. Pumps must turn for decades. Valves must open and close millions of times. Electrical contacts must remain clean. Seals must hold pressure. Computers must process data without accumulating hidden errors. Pipes must carry water, waste, oxygen, coolant, and nutrients without leaking or becoming blocked. Every component begins aging before departure. Some materials become brittle. Others creep slowly under constant load. Lubricants evaporate or chemically degrade. Polymers lose flexibility. Metals corrode. Insulation cracks. Bearings wear. Radiation changes electronics and weakens organic materials. No dramatic accident is required. Time performs the work. Engineers normally estimate reliability using laboratory tests, operational history, and accelerated aging. A component may be heated, vibrated, pressurized, or cycled repeatedly to approximate years of use. These tests reveal many weaknesses, but they cannot reproduce every interaction aboard an interstellar ship. Accelerated testing may expose a seal to high temperature for months. The real seal experiences moderate temperature, radiation, cleaning chemicals, vibration, changing pressure, and 50 years of contact with the same fluid. The difference matters. A material that survives each condition separately may fail when all of them occur together. Radiation can make a polymer brittle. Vibration then creates a crack. Cleaning chemicals enter the crack. Pressure enlarges it until the seal leaks. The final failure appears sudden. Its preparation lasted years. Redundancy is the first defense. If one oxygen pump stops, another should continue operating. If one computer fails, another should assume control. If one power line is damaged, electricity should reach critical equipment through a separate route. But duplication alone is not enough. Two identical pumps may contain the same manufacturing defect. Two computers may run the same flawed software. 3 sensors may share one power supply. Backup cables may pass through the same compartment and burn in the same fire. This is called common cause failure. It defeats systems that appear redundant on paper. True resilience requires physical separation, different technologies, independent power sources, and the ability to operate manually. A carbon dioxide monitor based on one sensing method should be checked by another instrument using a different principle. Digital controls need mechanical overrides where practical. Diversity creates its own cost. Different machines require different training, tools, spare parts, diagnostic methods, and software. Maintaining 3 pump designs may reduce common defects while tripling the number of components the crew must understand. The spare parts inventory cannot contain everything. A ship may carry hundreds of pumps, thousands of valves, kilometers of cable, and millions of electronic components. Storing a complete replacement for each item would add enormous mass. Predicting which parts will fail over 50 years is impossible. Engineers must choose. High-risk components need full replacements. Common seals, bearings, sensors, and connectors need large inventories. Other equipment may be designed around standardized modules that can be moved from non-essential systems to critical ones. Eventually, the crew will still need a part that was not packed. Manufacturing aboard the ship becomes essential. Metal printers and machine tools could produce brackets, pipes, gears, housings, and selected replacement parts. Polymer printers could create seals, ducts, containers, and medical tools. Electronic fabrication might repair simple circuit boards or produce basic sensors. Yet, manufacturing is not creation from nothing. A printer requires feedstock. A milling machine needs cutting tools. Heat treatment consumes energy. Precision components require measurement equipment. A replacement bearing needs material with the correct hardness, surface finish, and geometry. A part that looks correct may fail under load. Quality control, therefore, becomes as important as production. The crew must inspect dimensions, search for internal cracks, test electrical properties, and confirm material composition. Some parts should be operated under controlled conditions before entering a critical system. Testing may destroy the sample. If only one replacement can be produced, the crew may have to choose between proving its strength and preserving it for use. Electronics present an even greater challenge. Modern processors contain structures manufactured at scales impossible to reproduce in a small workshop. Radiation can flip bits, damage memory, and degrade semiconductor devices. Error-correcting memory can identify and repair many data errors. Shielding and redundant processors can reduce risk. They cannot manufacture an advanced chip after the reserves are gone. The chip may need slower, radiation-tolerant computers built from larger and more repairable components. Critical control software should be preserved in multiple independent storage systems. Documentation must include not only source code, but compilers, operating environments, circuit diagrams, test procedures, and explanations understandable to future technicians. A file without the system needed to read it is not knowledge. Data storage also ages. Magnetic media can lose information. Flash memory wears with repeated use. Optical surfaces can degrade. Cosmic radiation may corrupt bits gradually. Archives must be copied, compared, and corrected continuously. Checksums can reveal whether data has changed. Error-correcting codes can reconstruct damaged information when enough original structure remains. Multiple archives should be stored in separate, shielded locations. But software failure is not always corrupted data. Complex programs contain logic errors that appear only under unusual combinations of events. A valve closes late. A sensor freezes at a believable value. The controller responds correctly to each input individually, but makes the wrong decision when several systems fail together. These interactions are difficult to test on Earth. After departure, the crew becomes the development team. They must modify software without introducing new faults. Every update needs review, simulation, rollback capability, and protected copies of the previous version. A rushed correction during an emergency may restore one function while quietly damaging another. Mechanical systems can create the same cascade. Suppose a farm pump begins vibrating. Technicians reduce its speed to protect the bearing. Water circulation falls. Root zones receive less oxygen. Crop growth slows. The farm's carbon dioxide absorption changes. Humidity rises. Dehumidifiers work harder, increasing electrical demand and heat production. One worn bearing reaches the power system, atmosphere, thermal system, and food supply. This is why maintenance cannot wait for failure. Sensors should track vibration, temperature, electrical current, fluid pressure, chemical composition, and acoustic changes. Trend analysis can reveal degradation before performance crosses a dangerous threshold. Early detection creates time. It does not create unlimited labor. Inspection, lubrication, calibration, cleaning, software testing, and replacement consume thousands of work hours. As the ship ages, maintenance demand will increase. At the same time, the first generation of engineers will age, develop health problems, and retire. Younger technicians must take over systems they did not design. A procedure can describe how to replace a pump. It may not explain why a pipe was rerouted 27 years earlier, why one sensor always reads slightly high, or why a particular bolt must be tightened in an unusual sequence. Informal knowledge accumulates inside people. When those people die, part of the ship's operating system can disappear with them. Every repair, therefore, needs documentation. Diagrams must be updated. Temporary modifications must not remain temporary for 20 years without review. Students need supervised experience before becoming responsible for essential equipment. Education and maintenance become the same survival process. Even then, the crew must prioritize. They cannot preserve every laboratory, private cabin, recreational system, and scientific instrument forever. Some equipment will be dismantled so its materials can support more essential functions. The ship will slowly consume itself. A research telescope may become spare metal. An unused habitat may provide cable and pressure valves. Comfort decreases to preserve survival margin. Each sacrifice solves today's problem while leaving fewer options for tomorrow. Machinery. therefore may not cause the first death through one spectacular breakdown. It may narrow the crew's choices until an ordinary failure has no remaining backup, no compatible part, and no trained specialist. By then, the decisive resource will no longer be metal or power. It will be whether the knowledge needed to save the ship still exists inside its walls. A complete technical archive does not guarantee that anyone will understand it 50 years later. Information and skill are not the same thing. A manual can identify a damaged pressure regulator, list its components, and describe the correct repair sequence. It cannot give an inexperienced technician the touch needed to recognize a damaged thread, the sound of a misaligned bearing, or the judgment to stop before a stubborn bolt breaks. That judgment develops through repeated work. Earth continually creates specialists through universities, laboratories, factories, hospitals, apprenticeships, and professional communities. A young engineer can learn from thousands of earlier failures. A physician can consult experts who have treated rare conditions. A farmer can compare results across many climates and growing seasons. The Proxima crew has only the experience available aboard one vessel. During the early years, that experience will be strong. The original crew will have trained inside full-scale simulators. Many will have helped design or test the systems they operate. They will understand why certain materials were selected, where designers accepted compromises, and which components deserve suspicion. But those people will age. Some will die earlier than expected. Others will lose vision, hearing, memory, strength, or fine motor control. Radiation exposure may accelerate neurological decline in certain individuals. A stroke could silence the only engineer who fully understands the reactor's emergency control system. Replacing that person requires more than assigning a new job title. A small crew cannot maintain equal expertise in every discipline. One technician may know atmospheric chemistry, electrical control, and thermal management. One doctor may also manage radiation monitoring and reproductive medicine. One biologist may supervise crops, waste processing, and microbial surveillance. This arrangement saves personnel. It also concentrates knowledge inside a few vulnerable minds. Cross-training can reduce that risk. Every critical role should have several qualified replacements. Trainees should practice under realistic conditions, including failures that require manual control. Their competence must be demonstrated through action rather than confirmed by a completed lesson. Yet, cross-training has limits. Learning surgery requires years. So does reactor engineering. So does diagnosing a disease inside a closed agricultural ecosystem. A person can understand the basic procedure in several fields without possessing the deep experience needed during an unfamiliar crisis. The crew must decide how much specialization it can afford, train everyone broadly, and the ship gains flexibility but loses depth. Train a few people deeply, and the mission becomes dependent on their survival. The safest arrangement changes over time as people age, children mature, and equipment is modified. Education, therefore, cannot follow an ordinary school calendar. Children born aboard will need language, history, mathematics, science, medicine, engineering, agriculture, governance, and practical maintenance. They must also contribute to communal life, and develop identities not completely defined by future jobs. The ship cannot treat every child as a replacement component. Personal ability will differ. A young person expected to become a surgeon may lack the necessary coordination or desire. Another may show exceptional mechanical judgment, but be assigned to agriculture because staffing plans were made before birth. Forcing people into unwanted professions can damage motivation and trust. Allowing unrestricted choice can leave critical roles empty. Earth solves part of this problem through population size. Millions of people can pursue different careers, and institutions recruit those suited to specialized work. Among a population of approximately 100, the statistical variety is narrow. The mission may pass through a generation with no natural candidate for a particular role. Training technology can help. Virtual simulations can reproduce fires, equipment failures, surgeries, crop infections, and navigation emergencies without damaging the real ship. Interactive systems can adjust difficulty and record performance. Artificial intelligence can answer questions and guide practice. But a simulation inherits the assumptions of its creators. If designers never anticipated a certain failure, the training system may not include it. If the actual ship has been modified over 30 years, while the simulation remains unchanged, students may learn procedures for equipment that no longer exists in its original form. The archive must evolve with the vessel. Every replaced valve, rerouted cable, revised medical protocol, and altered crop variety needs documentation. Records should explain what changed, when it changed, who approved it, and why the old arrangement was abandoned. Without that history, future technicians may reverse an important repair because it looks incorrect. Too much documentation creates another danger. After decades, the archive may contain millions of pages, recordings, diagrams, sensor logs, software revisions, medical cases, and maintenance reports. Finding the correct information during an emergency becomes difficult. Contradictory versions may survive. A search system may return an obsolete procedure because its wording matches the question more closely. Knowledge must be organized, tested, and periodically simplified. Critical procedures need current versions stored separately from historical records. Crew members should review emergency instructions while systems remain healthy. Drills should reveal missing steps, confusing language, and dependencies that documentation failed to mention. Drills also expose forgotten physical skills. A technician who understood a procedure 10 years earlier may no longer be able to perform it quickly. A doctor who has read about an emergency surgery but never completed one may freeze when the patient begins bleeding. A command team that has discussed fire response may still communicate poorly through masks and alarms. Repetition keeps knowledge alive. However, practicing every unlikely emergency would consume most of the crew's time. The mission must choose which failures deserve frequent drills and which must remain primarily inside the archive. That choice can be wrong. Rare events are precisely the ones people are least prepared to handle. A pressure rupture may occur once in 40 years, yet the first response must be correct within seconds. A reactor shutdown may never happen, but one mistaken action during it could remove power from life support. Cultural change may weaken procedures further. The first crew will remember Earth laboratories where safety rules were developed. Later generations will know those places only from recordings. A warning written by a distant engineer may feel less convincing than the personal experience aboard a system that has operated safely for decades. If a valve has never failed, inspection may begin to feel unnecessary. If a fire drill has never revealed a fire, younger crew members may view it as ritual. When resources become tight, leaders may shorten training to gain more labor. Maintenance apprentices could be promoted before they are ready. Scientific education might be reduced so students can spend additional hours farming or repairing equipment. The decision provides immediate relief. Its cost appears years later. Language itself will change during the journey. New abbreviations, pronunciations, and technical expressions may emerge. Instructions written in the language used at departure could gradually become formal or unfamiliar. Even when every word remains readable, its practical meaning may shift. The crew must preserve a shared technical language. It must also preserve the habit of questioning authority. Blindly following an incorrect manual can be as dangerous as ignoring a correct one. Future technicians need enough scientific understanding to test claims, examine evidence, and recognize when conditions have moved beyond the original design. That ability is difficult to preserve because it requires freedom to make mistakes. Training equipment may be damaged. Crops may be lost during experiments. Young technicians may temporarily reduce system efficiency while learning. Leaders facing narrow survival margins may prefer to keep inexperienced people away from essential machinery. Then no one gains experience until the expert is suddenly unavailable. A resilient ship must accept small, controlled risks to prevent a larger generational failure. Knowledge loss is therefore not an isolated threat. It changes the severity of every other threat. A damaged carbon dioxide scrubber is repairable only if someone understands it. An unfamiliar infection is treatable only if medical reasoning survives. A constitutional crisis is manageable only if the community remembers why its safeguards exist. By the final decade, the most important systems may no longer resemble their departure designs. Repairs, substitutions, software updates, and material shortages will have transformed them. The people will have changed as completely as the machinery. They must still perform one operation that no generation aboard has ever practiced under real conditions. They must slow the ship beside another star, Arrival at Proxima Centauri will not mean the mission has survived. It will mean the crew has reached its most unforgiving test. For decades, the ship has followed a relatively stable direction. Course corrections may have been small. The habitat has operated under a predictable rhythm. The propulsion system may have remained inactive or at reduced demand for long periods. Then braking must begin. A propulsion system built on Earth, exposed to radiation, vibration, thermal cycling, and material aging must produce controlled thrust after decades of flight. Fuel must remain usable. Valves must open correctly. Guidance sensors must determine the ship's position and velocity. Radiators must reject the heat generated by the braking system. Failure may not produce a second attempt. If the ship is moving at a significant fraction of light speed, braking must start far from the destination. Waiting until Proxima appears close would make stopping physically impossible. An error discovered late could send the vessel through the system and back into interstellar space. The crew cannot turn around and try again. Navigation near Proxima presents its own uncertainty. From Earth, astronomers can study the star and its known planets. But a mission launched decades from now would still depart with incomplete knowledge. Orbits may be refined during the voyage, yet stellar activity, dust, small bodies, and local plasma conditions could differ from predictions. Proxima Centauri is a red dwarf known for powerful flares. Its habitable zone planet, Proxima Centauri b, orbits much closer to its star than Earth orbits the Sun. That closeness exposes the planet to intense stellar activity. Flares and energetic particles may threaten atmospheres, surface equipment, and human health. The destination may not offer a safe landing site. Even if the planet has suitable temperatures in some regions, temperature alone does not prove habitability. Its atmosphere could be thin, dense, toxic, or partially lost. The surface may receive dangerous radiation. Liquid water may be absent, buried, frozen, or chemically inaccessible. The crew must learn these facts before committing people to descent. Orbital observations may require months or years. Probes should measure atmospheric composition, radiation, weather, surface chemistry, and terrain. Robotic landers must test soil and identify resources. A settlement should not depend on one promising image or one ambiguous spectral signal. But waiting aboard an aging ship creates pressure. Food reserves may be declining. Machinery may need replacement materials. The crew may have planned its entire social system around establishing a colony after arrival. Some people may demand an immediate landing, while others argue that the surface is too dangerous. The mission's final technical decision could become its largest political conflict. Still, the question remains who dies first. No honest investigation can name the individual or the date. Human biology and complex machinery do not provide that precision. But the evidence does reveal the most probable structure of the event. The first death is unlikely to have one independent cause. It will probably emerge from a chain. Consider a coolant pump that has operated for 31 years. Its bearing begins degrading, producing a vibration too small to trigger the main alarm. A sensor detected the trend months earlier, but technicians classified it as calibration drift because similar warnings had been false. The experienced thermal engineer recently suffered a stroke. Her replacement understands the system, but has never observed this failure in real hardware. The current maintenance manual lists the original pump, not the locally manufactured bearing installed during the previous decade. The pump finally loses efficiency. Coolant flow falls through one equipment bay. Temperature rises inside an atmospheric processor. The carbon dioxide removal system automatically reduces capacity to prevent heat damage. A second scrubber should compensate, but it is already offline for regeneration valve repairs. Carbon dioxide begins accumulating. The increase is slow, and the central sensor reports a lower value than several personal monitors. The crew trusts the central instrument because its readings control the ship's official alarms. Headaches appear during the night shift. The medical team initially suspects a viral infection because 2 technicians also report nausea and fatigue. They isolate the affected workers. This removes several trained people from maintenance when the thermal system needs them most. A tired technician attempts to restart the scrubber manually. Elevated carbon dioxide has already reduced his concentration. He opens a bypass valve in the wrong sequence, allowing hot gas to damage a seal. Smoke enters the compartment. The fire is controlled, but one crew member inhales carbon monoxide and suffers cardiac arrest. The clinic begins treatment. Oxygen, intravenous fluids, medication, and continuous monitoring are available. Yet the patient's heart has also been weakened by years of radiation exposure. Resuscitation fails. What killed that person? The death certificate may record cardiac arrest caused by smoke inhalation. The engineering report may identify a damaged coolant pump. The environmental report may blame carbon dioxide accumulation. The training review may identify incomplete documentation. The command investigation may criticize delayed maintenance and excessive trust in a drifting sensor. All would be correct. No single failure crossed the ship alone. Mechanical aging combined with imperfect sensing. Imperfect sensing combined with lost expertise. Lost expertise combined with fatigue. Fatigue combined with atmospheric exposure. Radiation increased the patient's vulnerability. The first death came from the network. This pattern explains why ranking individual hazards can mislead designers. Radiation may appear less urgent than decompression because its effects develop slowly. Psychological stress may appear less concrete than a broken valve. Education may seem less essential than shielding, but each one alters the crew's ability to survive the others. The most dangerous system is not necessarily the one most likely to fail. It is the one whose failure removes protection from several other systems at once. Electrical power is one candidate. Without power, pumps stop, lights fail, crops lose photosynthesis, computers shut down, and temperature control weakens. The crew is another. When people become sick, exhausted, divided, or insufficiently trained, every backup becomes harder to use. This leads to a difficult conclusion about the mission. The first person may die early from an ordinary medical event that would also have been fatal on Earth. If that happens, the death will not prove interstellar travel impossible. The more revealing death would be one that Earth could have prevented. A treatable infection becomes fatal because an antibiotic degraded. A repairable leak becomes fatal because the correct seal was unavailable. A survivable fire becomes fatal because several crew members misunderstood the ventilation layout. Such an event would show that distance had removed civilization from the treatment. The ship must therefore carry more than life support equipment. It must carry the functions of a civilization in compressed form medicine, manufacturing, education, law, scientific reasoning, agriculture, archives, and the ability to revise failed assumptions. Even then, survival cannot be guaranteed. A perfectly designed vessel does not exist. Every kilogram assigned to shielding is unavailable for spare parts. Every additional subsystem creates maintenance. Every biological loop introduces variability. Every generation changes the society responsible for operating the machine. The correct goal is not to eliminate all failure. It is to prevent one failure from becoming irreversible. Compartments must isolate fire and pressure loss. Reserves must provide time. Independent sensors must challenge misleading readings. Multiple people must understand every critical system. Governance must allow bad news to move faster than fear or pride can suppress it. Most importantly, the crew must preserve options. A damaged farm should not immediately threaten oxygen. A medical emergency should not consume the only qualified engineer. A software error should not disable manual control. One political decision should not place the entire population on an untested surface. Survival margin is measured in alternatives. If the vessel reaches Proxima with functioning machinery, but no alternatives, it has arrived already defeated. If it reaches the system damaged, tired, and reduced, yet still able to observe, repair, debate, and adapt, the mission remains alive. The first death will matter deeply to a population of 100. It will leave an empty seat at every shared meal. It may remove a parent, teacher, doctor, engineer, or friend. It may force the crew to question the mission and the sacrifices still ahead. But it does not have to become the first step toward extinction. That is the final distinction. The success of humanity's first interstellar voyage will not be proven by preventing death for 50 years. No community can promise that. Success will be proven by ensuring that when death comes, the knowledge, trust, resources, and resilience needed to protect everyone else remain aboard.